Good morning or afternoon, everybody. Thank you for logging in today. We're here to see a presentation on Vitrek's products offerings for the semiconductor industry. And there we go. Yep. So here we go. A quick overview on the company. So Vitrek has been around for over 30 years. We are involved in a few different scenarios. So our core business with the Vitrek out of San Diego, anyway, was the electrical safety testing. So we're making fully automated high pot insulation resistance ground bond testers. These are often used for quality control and compliance. Another division we have is the power test and measurement side. So we do a 4700 precision high voltage meter that's capable of measuring AC and DC voltages up to about 140 kV, as well as a power analyzer, full feature harmonics power analyzer. 1 to 4 channels per chassis. They can be combined in networks to measure even more than that. So our high-speed data acquisition line, this is a gauge product. So we make high-speed digitizers. We have the ability to do RF record and playback. So we can actually take that RF signal, digitize it, record it, and then it could be sorted through to find whatever content you're looking at or looking for. Another aspect of the business, the MTI brand, would be vibration balancing. So we basically were the standard for some of the large frame aircraft engines. So the PBS system is going to allow you to identify how much weight and where to put weights on a big turbofan motor, for example, or turbofan turbine. So it could be dynamically balanced. And then we have non-contact distance measurement and displacement sensors, as well as lasers. Pretty much rounds out the portfolio. So we're in a lot of different industries, everything from semiconductors, obviously, power, lighting, mil-aero, motors and drives, green energy. I mean, if it needs to be measured mechanically, or if it has a signal that can be transduced into 0 to 25 volts, or it needs to be tested with high voltage, we can do it. So we also, because of our broad product offering, we have a pretty broad customer base. Anyone from consumer appliances, Apple, Sub-Zero, Whirlpool, people like that, to Intel, Coherent, Applied Materials, all these people that are both fabricating semiconductors and doing research on them. We're involved with a lot of LED lighting, photovoltaics, battery testing with Tesla. And then we sell to a lot of the compliance people such as UL, TUV, and a lot of government and laboratories, Sandia, Lawrence Livermore. So if at any point, we're going to have a couple different sections where we can pause for questions. So right now, if anyone has a question, you're more than welcome to unmute yourself and ask it, or you can just type it in the chat and someone will answer it for you. All right, now I'm going to hand it over to Dan for this section.
All right, thank you, Chad. Today, well, first of all, my name is Daniel Melchior. I work in the MTI Instruments division of Vitrek. Today, we're going to talk about some of the products that we offer for the industry. The first one, we use non-contact capacitance sensors. We offer a host of different capacitance amplifiers, probes, both digital and analog options. So if, with the semiconductors, you can use these for displacement, thickness measurements, material processing, and those types of things. And today we're gonna focus on our two turnkey solutions. First, our manual gauge is the Proforma 300i on the left here, and our Proforma 300 ISA, which is our semi-automated wafer measurement system. These are used to characterize and test wafers that are in process for thickness variation, and our semi-automated system can actually map your entire wafer for thickness, warp, global and local flatness, along with bow measurements, and those things, which are very useful when processing to do a check on your wafer to make sure that you're within all the tolerances needed for the next stage in microchip processing and manufacturing. So our 300i is a manual gauge. Let me get to the next slide here. Hold on one sec. Okay, so we do use capacitance technology. If you're familiar with capacitance technology, the standard technology requires you to have the sensor sense to a conductive grounded target to complete the circuit for the measurement. What we employ is we have an exclusive push-pull capacitance technology that we use for our systems, which do not require a grounded target, which is excellent for both semi-conducting and semi-insulating materials. So you don't need a grounded target or anything like that for that. So the measurement principles, with these tools, it uses opposing probes. Our push-pull probe is actually two sensors built into one probe body. As you can see on the left here, there's a signal that comes out of the push side of the probe, and it goes across the target to the pull sensor, which is it's run at the same frequency, but there's a 180-degree phase shift, which basically shoots the target down one side and then sucks it back up the other. We use one on the top of the machine, or on the top of the wafer, and one on the bottom. And you can see the math on the right is how we calculate both the thickness and the shape of the wafer as it moves between the two probes. So you can get thickness variation. There's a host of different measurements that you can do, but this is the technology used for that. Our Proforma 300i is a manual gauge. So basically it's small, it's probably the size of a big laptop. So you can put it right on your table or desktop. It has auto leveling. There's a bubble level. You can adjust it so it is parallel and flat for your surface. It's got a non-abrasive Teflon coated measurement stage. So you just place your wafer on top of the stage, and you can see that the wafer here is in between the probes, and the measurement is shown on the LCD display. So it does have a big LCD display. It does have a USB port on the front, so you can store and log your data for your thickness variation, and there's also a bow measurement that you can do with the Proforma 300i. All of our technology, both the 300i and the 300 ISA, give you an accuracy of 1/4 of a micron, and it gives you a 50 nanometer resolution. So this can be used for wafers with a 1700 micron or 1.7 millimeter measurement range. So the probes are adjustable. So if you do have a thicker wafer, you can adjust it, calibrate it accordingly, and get your measurements. So it does do thickness, 5-point TTV, which is total thickness variation, center bow measurement. As you can see, it does have a high resolution LCD display. There's also Ethernet and RS-232 computer interface. There's also a software data logger program. So if you have a stack of wafers that you're testing, you can store that through the computer program if you want to, or through the front USB port to save your data. Um, there's also these little pin guides which help you center your wafer if you're making a bow measurement. That is what that is for. So, and it along with semiconductor wafers, you could actually use this for any material as well. So if you have, sheet metal, for example, or some other kind of material, it will work the same as long as they are between the two wafers. So you don't need to use it just for semiconductor wafers, but um, it is that. So it's a great tool to have. It's a great thickness gauge monitoring. We have many customers have this just to do a quick check of thickness, down to the quarter micron level. So it is highly accurate. Um, but yeah, it's a great inexpensive alternative to a fully automated system. We do sell a lot of these units throughout the year, so it is a great product for us. And then here's a zoomed in picture of both the front keypad of the device, the display, and a quick snapshot of the data logger program. It does use a voltage from the top probe and the bottom probe, as you can see. And then you can export your data to Excel through a CSV file, save it through there. So you have all of that available to you. So it's a great tool to have on your workbench. The 300 ISA is our semi-automated inspection system. It does accommodate wafers between 75 millimeters and 300 millimeters. It does automatically scan your entire wafer, and it will give you a 3D map of your wafer for thickness and shape. So that includes, as you can see, thickness variation, bow warp, flatness. There's site and sorry. There's a couple other things in there that if you need more information, I'd be happy to share with anybody. But again, in standard range, it gives you accuracy to a quarter micron with a 50 nanometer resolution. With the system, we do have a strong software package. We do give a laptop with this. I'll go into the components in a second. And it does have Ethernet capability as well, so you can control this and monitor things remotely through the Ethernet. So it's got the network capability. And it does, as you can see with the features here, it does meet the SEMI and ASTM standards. You can see for thickness, it's the ASTM F533. Bow is 534, warp is 1390 if you're looking at home, and the flatness spec is to the F1530. So if you need more information on that, I'm happy to provide that. But those are the specs for this. Now you can see the size. It basically comes in 3 different components. The controller controls the measurement stage, and that's where the data is gathered and is sent to the laptop computer. The middle is the measurement stage there. You can see the size. It does fit, on a small table. You can move it around if you had to. But basically, it's like a big record player. So it's semi-automated in that you have to manually put the wafer onto the stage, but then you just press the button through the software. It spins the wafer around through the measurement stage, and gives you a precise map, X, Y data of your wafer. So you can actually see that coming through. So it's not a huge machine. Some of the other features, like again, it does use our push-pull capacitance technology. It does measure pretty much, I'm not going to say all, but pretty much all semiconducting and semi-insulating wafers. So it does include silicon carbide, obviously, silicon, gallium, indium, and other ones that are not listed here as well. So these do the standard wafers between 3 inches and 12 inches. It gives you a full 1,000 micron measurement range without recalibration. You can actually measure thicker wafers than this with probe adjustments, but the measurement range, the variation is up to basically a millimeter in thickness variation there. So it does meet all the ASTM standards. Um, and it does use the our computer interface that we give with the software is a Windows user interface. You can save data through CSV. There's a couple different options for that. So it does have Ethernet connectivity, and it does meet the SEMI standards for both health and safety and ergonomic compliance. So some of the biggest microchip manufacturers, in the world use this tool. They'll take wafers off their line, do a check to make sure that the shape is what they need for the next step in the processing. So this is just a quick overview of some of the software features. This is a lot summary. I know this picture is hard to see. This was a single wafer measured 5 times. It just kind of shows the repeatability of the thickness measurements here. So this is part of the software program that you see. So if you want to see the data in raw numbers, there it is. This is the median surface. So you can see for the same wafer, the median surface is shown here. This is a 3D model, so you can actually look from the top, the bottom, and then there's a little guide here that shows you, if there's any abnormalities or deviations from the center point. You will see that here. This is the median surface. Moving forward, here's a thickness outlook. This particular wafer only has a thickness variation of less than a micron, so this one is particularly flat. But if there was, we have seen some that look like, one of those Pringles potato chips. So you'll see it come up with a dip in the middle, and there's some with rough wafers. You see bumps in some cases. This is a pretty flat standard wafer here. This is the ASTM semi-compliant scan pattern. It is preloaded with the software. So this is a 300 millimeter wafer. This is all the points that the sensors will pick up. On this 300 millimeter wafer, you're getting about 3,200 measurement points around the full wafer, and then the center scan as well. So that is the scan pattern feature, and this is customizable. So if you do want to set up your own scan pattern, you can do that. If there's only certain areas of interest, say you wanted to look at just the center point, you could look at that as well. So there's a lot of different things that you can do with the software to customize exactly what you're looking for here. Again, this is the raw data points part of the software. You can see that there's 3,200 points here, and then as far as the XY of the map, you can actually take a look and see where you're at with thickness at different locations of your wafer. So you have a good map of shape of the wafer there. And then again, here's just a picture of, that's not me, but there's the laptop in the measurement stage. So you basically just use the mouse and it will start the machine and take your data right there through there. So if we have questions on this now, I'd be happy to answer any. If we want to wait to the end, Susie, that's fine. But if not, I'll throw it over to Gerald for the gauge line.
Okay, we are clear in the chats, so we are good to go.
All right.
Good afternoon. My name is Gerald Allgaier. I'm Systems Specialist for Vitrek, and I will also be joined by my colleague Andrew Dawson, Engineering Manager and Application Specialist, and we'll be going over the Gauge brand of products that can be applied in the semiconductor industry. So our Gauge brand is known for our high-speed digitizers that can capture and digitize high-frequency signals. with high resolution and accuracy. In semiconductor manufacturing, they're basically essential tools for capturing and analyzing fast electrical signals with high fidelity. And they enable engineers to basically observe and measure the behavior of devices and circuits in real time. And that provides valuable insights for like design validation, performance analysis, and troubleshooting. Their high performance, including maximizing the effective number of bits over a wide signal frequency range, help provide real-time data on the device performance and behavior, thereby improving the efficiency and accuracy in the manufacturing process. And them being PCIe-based devices, our digitizers can be easily integrated in open PC-based platforms with the capability to stream acquired data in real time to either host CPU or GPUs for signal processing and or signal recordings. So in the semiconductor industry, our high-speed digitizer usage generally falls into three main categories, and that is real-time process control, material inspection, and functional testing. For real-time process control, it's the fast download speeds of the acquired data that allow for the rapid real-time characterization testing of the semiconductor fab process. And here, the advantage of our digitizers is their short data latency that allows them to participate in fast device control loops. For the material inspection, our digitizers are generally used as a part of a non-destructive test system to effectively inspect wafers for potential flaws or defects. And here the advantage of our digitizer is the ability to capture signals at high speed with high resolution for digital analysis. And in the functional testing, that's where chips are basically rapidly positioned into text fixtures, where there are high-speed test signals that are acquired at key test points, and the chips under test are either flagged as being pass or fail. And here the advantage of our digitizers is their rapid download speed with the ability to quickly switch ranges for fast test switching. In the next couple of slides, my colleague Andrew Dawson is going to review some of the specific customer use cases for each of these categories with our digitizers.
Hi, Andrew Dawson here. I apologize, point of order here. We've got some construction going on outside, so I'll try and speak over that. As Gerald said, I'm going to take you through about a half dozen applications here. We'll sort of go through the semiconductor manufacture process and highlight the applications in which the gauge card finds itself. I should say that our gauge digitizers are very general purpose, and we don't really have any specific features for semiconductors per se. But as you'll see, we find the gauge card in quite different applications at many different stages because of its very general purpose ability to capture high-speed waveforms from different sorts of probes. So to begin, we'll talk about this real-time. This is right at the beginning at the semiconductor fabrication facility. So they start with what you may have seen, a raw semiconductor wafer. These are typically, I think, about 1 foot to 2 feet in diameter. These are the biggest and most pure single crystals of any element that we can make. We've been making pure single crystals of silicon for so long. We're really excellent at it. And what they do in these fabrication facilities is deposit impurities into the pure silicon to dope it, as we know, N and P type doping, and to build various complex structures, processors, and so forth. So basically, they deposit this onto this large wafer, and then afterwards saw it up into little pentiums or whatever they are. So the gauge card is used to control one of these deposition, pieces of deposition equipment. Normally, the gauge card is used to acquire data and then analyze the data in post-processing, where there's no real rush to get the data analyzed. This, however, is what we call a real-time application, which is kind of defined as one where you need to get the answers. You need to analyze and reduce the data, kind of get the answer as the measurements are occurring, because you're actually having to act on it. one particular example we always bring up is when you're in your plane and there's a missile bearing down on you and you want to spoof it. You've got to read the signals from the missile and react quickly to spoof it before it blows you out of the sky. So similarly here, as the very fast deposition equipment is going along, it's got to be controlled based on feedback signals from certain sensors. So the customer has 8 sensors and originally started out with our 8-channel card streaming the data continuously. So this customer will take like one trigger and then acquire continuously for literally days as this process of deposition continues. And initially, as I say, they were acquiring the data and getting all the raw data off the card, which is the card was particularly perfectly capable of doing. But it turned out it was this like fire hose of data, which they couldn't manage. They couldn't process the data quickly enough to be able to consume it all. And indeed, we're only able to analyze about 10% of the data. So they'd take a chunk of data, analyze it and reduce it, and then they'd miss 90% of the rest of it, and then take another chunk. So this, presented problems for their closing their feedback loop. So what we did for them, our cards are controlled by what we call an FPGA, a field programmable gate array. Normally, instrument cards like ours would be controlled by a much simpler and general purpose multiprocessor. The problem is we need to move data around our cards so quickly from the ADCs to the memory and to the PCI bus at rates of several gigabytes per second, and you just can't do that with a microprocessor. So the FPGA is more like, it's a big chip that is more like configurable circuitry, software configurable circuitry. So instead of data moving around as controlled by a CPU, it's more flowing through circuitry in a pipeline fashion, which can be move data hundreds and thousands of times faster. Now, this FPGA is less than half full with sort of standard gauge functions. And up until maybe 15 years ago, we just concentrated on getting the raw data to the user as quickly and in as easily to use a fashion as possible. But we started putting in, for that 15 years, started putting in data processing firmware. We call it firmware because it's in between software and hardware. And we've got several canned firmwares that the customer can obtain. One for example, signal averaging, one for FFTs, one for digital down conversion, and others. What I say is that the FPGA is really good for data reduction, for separating the wheat from the chaff. In the farming business, right? They literally separate the wheat from the chaff before sending the grain to the mill, and that's because they don't want to pay for the expense of transporting the useless chaff to the mill. The more refined operations, grinding and so forth, are done at the mill, but you really want to get that weight down. In a similar way, the FPGA is best used for getting rid of the garbage that you don't want, so that only the data of interest are relayed across the PCI bus to the customer. So in this example, the firmware that we developed for the customer picks out things like amplitudes and zero crossing positions of the waveform. And you can see how if you have thousands of points and reduce that to a single amplitude, you can get huge reduction factors. And indeed, we were able to achieve a reduction factor from this data that's coming in on 8 channels at 500 megasamples per second. We achieved a data reduction factor of about 150. And by doing that, that reduced the processing load on the host CPU. It had to deal with 150 times less data, and this pre-processing step, the burden of this pre-processing step was alleviated. So by doing that, they were able to go from consuming and processing only 10% of the data to consuming 100% of the data, and that worked in their, was able to work in their control loop. Another angle of this real-time application that isn't obvious and isn't relevant in post-processing applications is the data latency. How fresh is the data? Okay, because if the data is too old and you're trying to control the process on it, you might be sort of closing the barn door after the horses left the barn, sort of thing. So we were able to achieve with this firmware, because it's so fast, latencies of only a few milliseconds, sorry, which was sufficient for the customer. So really, that went from an application without the firmware that couldn't be done to one that could be done with the powerful effect of this data reduction firmware that, as I say, reduced the fire hose of data to a sort of a drip, drip, trickle. So moving along, as I say, from the fab process, the next stage is inspection of chips of the dies during packaging. So the next application here is an important one. One of the main functions of the package, other than getting the connections of the electrical connections on the die out to the user, is for dumping heat. So the silicon die, that's again been chopped up from the fabricated silicon wafer, has to be well bonded to the package so that it can dump its heat. So what this customer builds is an ultrasonic inspection system to assess the bonding of the silicon die to its packaging. And the way it does that is, when bonding is really good, sort of the interface between the two components being bonded, in this case the packaging and the silicon die, isn't there, and the sound goes right through the bond. However, if the bond is lousy, if the glue isn't sticking, or if there's some sort of delamination, this presents a reflective interface for ultrasound. So in fact, the amplitude, if you look at the place where you expect, you sort of know where to expect the echo from the interface between the die and the package. And if you look there, the amplitude of that echo is a direct measure of the poorness of the bonding. You can then scan parallel to the die surface, and then produce a map, a color-coded map of the bond quality over the entire surface of the die. And if it's you can actually produce a kind of an average bond quality index that then is used to produce a pass-fail criterion for the chip. In the scan, which might be several thousand points by several thousand points, the data are streamed off of the card very quickly. In the old days, you'd have to stop, download the data, whereas now with our streaming technology, we're able to offload the data from the card as it's being collected for the very fastest scan time. So that's another big advantage of the gauge card, is its fast data transfer speed for fast scanning. And of course, the high resolution to get the very smallest echoes from that bond to really judge that bond quality as best as we can. Next. So this is an interesting one, again, during the fabrication of MOSFET chips. So you package up your MOSFET chip, and in order to characterize it, you can run relatively expensive characterization techniques like X-ray or ultrasonic inspection. But this customer does a fairly novel technique to judge the quality of the MOSFETs. The MOSFET is excited in various ways by DC and AC signals, and then they listen to the device listens with the gauge card to the noise signals coming out of various pins on the MOSFET, and specifically the frequency spectrum of the noise. And certain noise spectra can indicate signatures of key failure modes. I don't know to what extent that they actually understand why these noise, certain failures lead to certain noise signatures, or they might just do it phenomenologically, right? You can create a bunch of chips with known defects and then just look at if they look any different than regular chips. Anyway, as I say, it's very important that the card, they use a 4-channel card, 16-bit card, to get the very best signal fidelity on 4 channels, so that you can run 4 chips in parallel at the same time. And it's very important that the card has a very good frequency flatness, because you want any frequency variation that you measure in the noise spectrum to be indicative of what's going on in the chip and not on the card itself. So that's an important demand that the card met for that reason. So that's our second inspection application during the fabrication of chips. Moving on. Now we have a couple of functional tests. That's where you take the finished chip and put it into some sort of jig and see if it works as it's supposed to. In this case, the customer makes DC power conversion chips that, amongst other places, find themselves inside your telephone charger. Indeed, I think they brag that, not unlike spiders, you're never more than 6 inches or 12 inches or something from one of their chips, even though you might not recognize their name. So they have one particular test on their power chips that requires the chip to trip at a certain limiting current. So they, at relatively high speed, they ramp up the current, and then basically the line should be open once the current exceeds a certain very precise value, which of course they turn into a voltage to measure with our card. So they use actually one or more of our 4-channel cards so that they can probe 4 chips in parallel testing. They have an elaborate, a chip mounting system that gets the chip into the jig, and they can do 4 or 8 at a time. And so in our case, our high resolution and very high DC accuracy was very important to them to measure that trip voltage, which corresponds to a trip current, very accurately, and also our ability to allow multiple digitizers to work together seamlessly so that they can test several chips at the same time. Next. Yeah, next slide. There we are. Okay, so people who, oh, too far. People who've worked in the semiconductor industry may know the curve tracer. Okay. Sorry, can you hear me?
Yeah,
Yes.
we've got
Okay, I'm back a couple of slides there, but I'll start anyway, right? The one on the curve tracer we're on, I'm seeing the digitizer products here. So I'll continue. The curve tracer is a device that that applies control, normally applies DC voltages to a transistor chip and then measures currents. And typically there's a couple of control voltages and one measured current. So you may have seen one of these analog devices way back in the 60s or even earlier. Looks like an oscilloscope, but it produces these elaborate traced curves that characterize the transistor. So as I say, normally it applies DC voltages, but this customer makes a device for users characterizing silicon dies in R&D. And as we learned in the previous application, an unpackaged die has problems in that it overheats. It doesn't have anywhere to dump its heat. So basically, when these researchers are making candidate transistor dies, they can't hook them up to a conventional curve tracer to characterize them because they don't have the capacity to dump their heat. And so if you applied the DC voltage the conventional curve tracer does, the die would overheat and burn. So rather than forcing the researchers in R&D to go to the trouble of packaging their chips, what this customer does is makes a curve tracer that only applies a very short pulse instead of DC voltages. So it might apply a pulse of a microsecond or two every millisecond, thereby reducing the power that's applied to the die by a factor of 1,000 to where it doesn't overheat. So they can measure the same curve tracer curves, except without overheating and burning the die. So, so for that they they embed our digitizer within the instrument that they sell, and they need 4. I believe each one needs at least 2 channels, but they do use. So I think it's 2 channels times 2, so that they can use. They can do multiple chips at a time. I may be wrong about that. It may be 4 channels per per chip, and then they use multiple cards embedded within their device. And of course, having the 16 bits and high accuracy is important for this measurement because they do actually measure absolute voltage quantities, which they turn into currents and so forth. So that's an interesting application. Next, I believe, is the last one, which is a customer of ours that makes magnetoresistive disk read heads. Okay, these would formerly, before the 1990s, have been a very small coil to read the magnetic domains on the hard drive. Nowadays, we use something that was discovered in the 90s, or maybe a little earlier, developed in the 90s, which is something called giant magnetoresistance. The slides one ahead, if you could run that one back. So both sorts of reeds heads, the old coil and the magnetoresistive head, actually, it's interesting. I always assumed that a disk drive, the inner cavity, was evacuated to avoid air pressure. Apparently not at all. There's gas in there because the head actually flies like an airplane wing, glides over the surface of the disk, and only flies at a couple of nanometers above the disk in order to get the greatest resolution. The closer you are to the disk, of course, the smaller domain you can write and read. So what they do then is in manufacturing testing, they run the hard drive and they read back signals from a known pattern written on the hard drive and compare it to what the known pattern is. But at the same time, they can look at the raw read head voltage with the gauge card and make sure that that's right. So they use it during development as well to develop their disk reading algorithms, but also in production to make for quality assurance. Again, they use a 4-channel digitizer so they can run 4 of these heads in parallel. We actually developed also for them, custom firmware that allows for calculation of a data histogram on board the card, since all they need ultimately is a histogram to determine the nature of the signals that come off. The histogram is enough to characterize basically the head, whether it's a pass or a fail. So with that, those are the 6 applications that we could come up with for the semiconductor industry in those 3 domains we discussed. With that, I'll pass it back to Gerald for some information on the gauge cards.
So here's our table matrix of our current digitizer product models, detailing the A to D resolution that go from anywhere from 8-bit to 16-bit. Number of input channels from 1 to 4 channels per card. You can have multiple cards in a system. The maximum sampling rate per channel from 250 megasamples per second per channel, all the way up to 6 gigasamples per second per channel. Amount of onboard memory from 2 gigabytes to 16 gigabytes, depending on the model. The PCI interface type, and the current starting at pricing for these model families. All of our digitizers come included with our GaugeScope Lite Edition PC oscilloscope software, and that package does not require any programming. It's a GUI-based application that any customers can utilize with the products to visually see their acquired data. And they also come complete with our full library of software development kits that include C, C#, Python, LabVIEW, and MATLAB. And these software development kits are utilized by our customers to develop their own customized applications that are optimized for their specific requirements. The SDKs come with pre-built examples complete with source code that are fully commented for the developers to follow to make it easier for them to start to develop their custom applications. So with that, we'll open it up for any questions for any of the gauge-based products.
Okay, we are clear on the chats.
All right, then I'm going to go ahead and then pass this along to Chad to present the Vitrek products.
All right, guys, I'll just quickly run through some of the Vitrek products here. So obviously earlier we talked about our power analyzers. We make a full suite of power analyzers, are capable of measuring up to 500 harmonics, anywhere from microamps to 1600 volts and anything in between. We can obviously add CTs and PTs and extend our measurement range to pretty much anything within reason. So the DL series of electronic loads, it's a newer product for us, developed and manufactured here in San Diego. Its specialty would be, very high transient loads. You're going to get a built-in, data logger and O-scope with this thing. It's a really nice full-featured electronic load if you guys are making power supplies or want to test some power supplies that you guys are, maybe buying for your applications. On the next slide here, we can wrap up any questions. It sounds like there's probably not any because I didn't see any come through. So here's some more detail on the PA 900 family. So there's the 900, the 910, and the 920. All of the cards store their own calibration data. So you could swap in whatever you need, from a high current card to a high bandwidth card to a higher in voltage card. The most common is typically the AD, which would be our most accurate version with a dual shunt. It's got a 1 amp and 20 amp internal shunt. Like I said, all of these will go to 500 harmonics. That's standard. And you can add channel cards as needed. It takes about 5 minutes to install. And each chassis will hold 4 of those cards. So one of the keys here is there are 6 different models available. So it depends on your power levels and your voltage. So when it comes to voltage, you can either have a 0 to 150 or a 0 to 500 volt DC power supply. So there's obviously trade-offs there. If your whole purpose would be, sub 15 volts, definitely go with the 125 volt. Otherwise, the 500 volt is great. You're going to lose a little bit of bottom end performance, but not that big of a deal. And then they're basically available in a quarter, half, or full builds. So the 125 watt, 250 watt, and 500 watt. And that is your RMS power. Transients are going to be well in excess of that for a second or even less. And it's fully specified in the manual. If anyone has any questions, please reach out to me. I'm more than happy to answer them for you. So here's some information on the CHIPS Act. I'm sure everyone's heard about it. Hopefully this will help bring some manufacturing and some design back to the U.S. You guys can read this on your own at any time because you're all going to have copies of this.
Thanks, Chad. I just wanted to chime in real quick on the CHIPS Act. It was signed into law last August. As Chad said, to revitalize U.S. manufacturing. It should create, new good-paying jobs and again bolster our national security by nearshoring, the semiconductor manufacturing, bring it back to the U.S. It provides over $50 billion for semiconductor research, for development, manufacturing, workforce development. It also provides tax credit for capital expenses. So if you are looking to purchase capital equipment, for semiconductor manufacturing, that's something to keep in mind that it does provide a tax credit for that as well. Initially, they've seen a big increase, 116% increase in manufacturing in the U.S. And some of the big companies, Micron, Intel, Qualcomm, Global Foundries, they've already announced over $50 billion in manufacturing investments in the U.S. And these companies and even the smaller companies are going to need these tools for wafer metrology, material inspection, capturing, the fast electrical signals in real time and real-time process control and functional testing. So, the Vitrek family can offer a lot of these products to you, via our sister company. So it's something to keep in mind when looking at this. So just throw that out there. But this will all be available for if anybody wants part of this presentation. I'm sure we can accommodate that. But yeah, I'll turn it back to Susie if there's any questions, and we can go from there.
Okay, thank you so much, guys, for presenting. Yeah, we will go ahead and get everyone a copy of the presentation, as well as a link to the recording. If you go on to the very last page of the presentation, we've got everyone's contact information. You can always email us at the info@vitrek.com email address, or if you want to specifically speak to one of our presenters, we've included that here as well. If you have any questions, feel free to reach out to us, and we appreciate your time, and we hope you have a great afternoon.